Okay, this is the um, momentum overview continued. Several more points to make on momentum. First of all, regarding collisions, the classic example being pool balls. If we have, for example, a two-dimensional collision where ball number 1 blue hits ball number 2 red off center, then ball number 1 will be um, deflected in a downward direction, and ball number 1 will be deflected in an upward direction. And in such a collision, to very good approximation, the momentum before and after the collision is conserved. And so, in other words, the momentum of the blue ball plus the red ball before the collision is equal to the momentum of the blue ball plus the red ball after the collision. And again, it's very important to remember that momentum is a vector quantity, and so with the stipulation that the red ball before the collision has zero velocity is at rest, then this first equation simplifies to the second one, which means that these two final momentum vectors need to add to the initial momentum vector. And I've sketched approximately a situation where that's true. You can see that the two y components cancel each other, because since there's no y component here, and then the x component of the red plus the x component of the blue after is then equal to this. A simpler example would be a 1D collision, and the simplest case to consider is the one where if you've played pool, you know if you hit a ball at rest head on, that the first ball will hit the second ball, and then the first ball will then, after the collision, be at rest, and the second ball will have the same velocity and therefore the same momentum as the blue ball did. So in other words, they just exchange momentum. Next concept in this chapter is the concept of impulse, and that is taken from delta P over delta T is equal to F. Expressed differently, that's delta P, the change in momentum, is equal to the force times the change in time. Last concept in the chapter is the concept of center of mass. And so just intuitively, the center of mass is the balance point or center of geometric center. If there is an obvious geometric center, that's where the center of mass will be. We'll see how to calculate that, but the important property the center of mass has is if you have a system, the center of mass of a system moves as though the external force acts on a single mass, which is the total system mass concentrated to the center of mass. And so an example here is one of a wrench that's being slid across the table, and the table is either very low in friction or frictionless. Probably very low is a more accurate way to state it. The white dot is the center of mass, and you can see, although the wrench, the system of the wrench is undergoing a complicated rotation, the center of mass is going in uniform motion. In other words, it has a uniform velocity, which is a characteristic, of course, of there being no force.